Alright, so we are going to talk about what are called standing waves. And we're back here looking at this string. It's got a fixed end, and we have a ruler set up. We'll be doing this in class with some slinkies. I'm just going to push play, and I'll push play and see what happens. So the frequency, oh yes, frequency is super low. So as we up the frequency, this thing's moving slowly and it's creating some waves. There's a little bit of damping in there, but I have some specific values that I'd like to show you. Where are those? Aha. So if we put that on pause and let's go to 0.86 hertz. All right, so we're looking at this in the bottom part of your screen. I know you can't really, well, you can see me. Hi. But if you look at the bottom of the screen right here, 0.86 hertz. Okay, so we're gonna play this, and what is going to happen is this thing moves up and down, and it sends a wave down the string, and when the wave gets to the end of the string, it bounces back. And what happens is we can set up a pattern. So this is a standing wave pattern. Well, let's just watch what happens and let's see. Okay, so we have waves moving down the string and bouncing back, and you see this kind of repeating pattern where in the middle, if you're looking at the cursor, in the middle, this section, it is moving some. This isn't perfect, but it doesn't move a whole lot. And with a slinky in class, we can actually do better than this. But if I pause at a certain spot, you see we basically have one complete wave. So we could say, in this case, that the wavelength is about 7.5 centimeters. And we have this standing wave pattern. So it's up, and then it's down, and then it's up, and then it's down. This region here we call an antinode. So that's a region of maximum displacement. And then the region in the middle we call a node. So that's a region of minimal displacement. And then out here we have another antinode. So I'll push play again, and you see this pattern repeating itself where we have maximum displacement, minimum displacement, maximum displacement. Okay, and that was at a frequency of 0.86 hertz. So I'm going to double that up to 1.72-ish. All right, and then push play, and we're going to see what happens. So it gets crazy for a little while, but then we see this nice repeating pattern. Aha! So if I can push pause for a second, and it's like we have one complete wave. So if you're looking at the cursor, one complete wave and then two complete waves. Okay, so we doubled the frequency and we doubled the number of standing waves that we have set up. Cool. So you might be thinking, well, what happens if we go the other direction? Good question. So half of 0.86, I don't know why I needed to look at that, but half of 0.86, we got yeah, that was right, 0.43 hertz. So let's push play. It's going to be crazy for a little bit, but then we get this standing wave pattern. Aha! So I'm going to push pause. So we have, in this case, the ends of the string are nodes, and the middle is an antinode. And you see how we have 1/2 of a complete wave. So if I could extend the cursor over to the edge of the screen, but that's off the screen, right? It would be, we could see the other half of the wave. So we can push play again, and we see this. And there's a little bit of damping. So let's see what happens if I take the damping out. All right. Are you ready? Yes. So we take the damping out. So what's happening is the wave is transmitted here and it bounces back. Wave is transmitted here, bounces back. And because there's this repeating pattern, what's happening is we get one wave coming in, and then that wave bounces back. And by the time it's back here, it's adding to another wave. And those two bounce back. And then it's adding to a third wave. And those bounce back, and they're adding to a fourth wave. So we get this radical increase in amplitude, and that is called resonance. So radical increase, I think the string's going to break. Radical increase in amplitude. Let's bump up the amplitude. All right, this is an unbreakable string. But anyway, so this is what happens. We got no damping, and in reality, you know, when we're talking about sound waves or waves in a guitar string or something like that, there is a little damping, there is a little friction, so you don't get quite a dramatic effect as that when we're talking about resonance. But we do definitely, and we'll see this in class, we have situations where the dimensions of the system are such that the sound waves overlap, and you get this, when we're talking about sound waves, you get this increase in amplitude. If we're talking about lasers, so that's a light amplification by a stimulated emission radiation, and I'm looking at the numbers here, 0.86, this is where we were. So you can get light waves that do the same thing, and then they create this high intensity beam. So they overlap, and we get resonance. So here I put this back to 0.86. This is where we saw one complete wave. So we'll push play. We'll get this one complete wave set up. All right, so it is resonating. And if we were to take out the damping, hopefully we're going to see some large increase in amplitude. All right, so we still have the nodal region, a node right here, so minimum displacement. But at the antinode, woo, lots of displacement. All right, that's kind of cool. And then let's get all crazy and double, so we go to 1.72 hertz. Doubling the frequency, we'll push play. No damping, well, actually, okay, just to get the standing wave set up. And so this is where we saw two complete waves over the course of the string. And then we take the damping out, and it should kind of go crazy. But you see this repeating pattern. Nice. So we have a node and a node and a node. Big amplitude. All right, let's see if we can break the string. Bump up the amplitude. What happened? That's weird. All right. Well, there we go. Right, and so this isn't perfect. The fact that this moves up and down means that one complete wave isn't sitting here. But what I can do is adjust the frequency a little bit. So I was experimenting with this, and if it's a little off, it'll go maximum displacement, and then it'll cancel out for a little bit, and then maximum displacement. So this might be that situation. So we get a whole lot of constructive interference, and then we get this destructive interference when the waves cancel out for a moment. And if we were to get farther away from the resonant frequency, it should happen more quickly, right? So we get minimal displacement and then maximum displacement. So destructive and constructive interference. Cool. Let's see, how do I push